Welcome back to our PNG 332. This is the lab number 3 of our class. This is going to be virtual lab. So what I'm going to do is I'm going to go over the uh, PowerPoint presentation regarding this lab, and then I'm going to go over the manual with you guys, and I'll show you how we are going to collect different information required to do this lab using PVT simulator. And then at the end, I'll provide you with all the information required to complete this lab. And then your job is to go over the PowerPoint presentation, read the lab manual carefully, and then with the information given and the instructions that are already posted on the eCampus, you are going to complete this lab. Unfortunately, we don't have access to, you guys don't have access to the PVT lab simulator. So I thought this is the best way to perform the lab, and this would be the same when if even if you were in the class, because I was going to do the lab and then you were basically following me. So in this step, you just reserve that time for later on when we go back to school. You can go to the computer lab and then practice this for yourself. But for the sake of completing the lab number 3 of our class, this is the procedure that we are going to follow. So the lab number 3 is basically finding the fluid properties of the multi-component hydrocarbon fluid using PVT simulator. So if you review our chapter 10 slides and the video which is posted on YouTube channel, we have covered 5 different experiments that people do in the lab to come up with the PVT information. That was the compositional measurement, flash vaporization, differential vaporization, separator test, and the viscosity measurement. In this case, we are assuming that the compositional measurement is given. So for this lab, you are going to have a mixture of 3 components. That's methane, propane, and hexane. So we have a multi-component mixture. And then what we are going to do, we are going to start with the flash vaporization. And if you review our lecture, you will see that in the flash vaporization, the whole point was to find the bubble point pressure of the mixture and generate the table of pressures versus the relative volumes. Okay, and the relative volumes were basically the total volume of the fluid at any pressure divided by the volume of the fluid at the bubble point. And then we are going to perform the separator test, or what we call liquid expansion test. And we are going to perform the differential vaporization test or gas expansion test. So I'll go over those, and then I'll show you how to combine these properties to come up with the hydrocarbon fluid properties from the reservoir condition all the way to atmospheric condition. So in this task, we are going to start from the reservoir condition, from the reservoir pressure, and then we calculate three major parameters. That's oil formation volume factor, gas formation volume factor, and solution gas oil ratio, from reservoir pressure all the way to atmospheric pressure. And from our lecture materials that we cannot do this in one step. Any fluid properties that we calculate, we have to divide it in 2 steps, from reservoir pressure all the way to the bubble point pressure, and from bubble point pressure all the way to the atmospheric pressure. So I'll show you the step-by-step calculations and how we are going to perform this. So to start, as usual, the motivation is it's necessary part of petroleum engineering to be able to determine the relative surface volumes of oil and gas to reservoir volumes, and vice versa, because we always wanted to know how much oil in place and how much gas in place we have, and we always want to know out of that oil and gas how much we can produce and sell. So to do that, we need to have these 3 most important parameters, which are the oil formation volume factor, which basically shows the volume of oil and dissolved gas at the reservoir condition divided by volume of oil at the stock tank. So it basically shows how much oil will shrink when it comes from the reservoir to the surface. Gas formation volume factor, the same concept, shows how much gas we have at the reservoir condition in compared to the amount of gas we will get at the standard condition. And also you have the solution gas oil ratio, which basically shows the relative gas over oil produced at the surface. So these are important parameters that we are going to find. And as we already discussed this in the chapter 10, to do this, we are going to combine these three experiments: the flash vaporization test, differential vaporization test, and the separator test. So we said the flash vaporization is performed to find the bubble point pressures. For that, we are going to record the total volume of oil and gas at any pressure. Okay, so at any pressure, as we drop the pressure, we measure the total amount of gas and oil. And then after we find the bubble point, we also record the bubble point volume. And then we are going to divide all these volumes that we measured at any different pressure by the volume at the bubble point. Okay. And then we are going to perform the flash expansion of a sample, which is basically that liquid expansion. So in the liquid expansion, what we are going to do, since in the flash vaporization test we have already obtained the bubble point pressure, we are going to start from the bubble point pressure, and then we are going to send some amount of liquid out of the cell while we keep the pressure constant. Okay, and then when we send that amount of liquid out, we will see how much oil and how much gas we will collect in our separator and in our stock tank. Okay, and we collect the information regarding that. And after that, we are going to perform the differential vaporization test or gas expansion test. And in the gas expansion test, again, we are going to start from the case that we have a bubble point pressure at the reservoir. And then this time, we are going to drop the pressure in the reservoir or in the cell. And as we drop the pressure, some gas will come out of the oil. We are going to measure the amount of gas, the amount of oil in the cell. And then we are going to use the servo pump, and we are going to release the gas from the cell while we keep the pressure constant. And then we measure the quantity of the gas outside the cell. So when we have all this information, as will be discussed through the instruction, we are going to combine those to come up with the properties. If you remember from our chapter 10, we always combine the flash vaporization test with the separator test to come up with the properties above the bubble point, and then the differential vaporization test and the separator test to come up with the properties below the bubble point. So when we do that, at the end, we are going to have the oil formation volume factor as a function of pressure. So oil formation volume factor, as you know, it goes up as we go from the reservoir pressure and decrease the pressure to the bubble point, because oil swells. The pressure, you drop the pressure, oil swells. And after that, oil starts shrinking because after the bubble point, the gas starts coming out. So you will see these two behaviors above and below the bubble point. And then we are going to plot the solution gas oil ratio, and we will see, as the literature says, above the bubble point, the gas oil ratio will stay constant, and after we hit the bubble point, the gas oil ratio will drop, because some gas will release from the oil at the bubble point, and the amount of gas inside oil will be less than the bubble point pressure. Okay, so as we drop the pressure, the amount of gas dissolved in oil will be less, so the amount of gas which comes out of that oil at the surface condition would be less. And then at the end, we can also calculate the gas formation volume factor. We know we will not have any gas formation volume factor above the bubble point because there is no gas, all liquid. But below the bubble point pressure, the gas formation volume factor has an exponential function, exponential relationship with the pressure. Okay, so these are the three outcomes of this experiment. So formation volume factor of oil, gas formation volume factor, and the solution gas oil ratio. However, to do this, we are going to use a kind of modified version of the equations that we had in the book. So because of the dimensions has been changed, and here you are always working with cubic centimeter and with the SI unit, while in the class we're using in the field unit. For this lab, we prefer to use these equations to come up with the properties. So here, the oil formation volume factor BO is defined as small VO, okay? Which, if you look at it, it says it's a meter cube over meter cube, okay? Or centimeter cube over centimeter cube. That's a normalized volume, okay? That's a normalized volume of oil, which is coming from your flash vaporization test. That's basically the volume of the oil and the gas at any pressure divided by volume of the fluid at the bubble point. And then we have this parameter called CBF. So the CBF is a compaction factor, okay, which I will show you how to calculate that constant in the instructions, okay. So this will be a constant that we will calculate, and then if you have the VO, we can find the VO values. For the RS, again, the RS solution gas oil ratio at any pressure will be initial solution gas oil ratio minus F, the capital F, which is the cumulative relative gas volume at a standard condition, divided by that CBF value, okay? Again, the CBF is a constant, F we calculate at any pressure, and RSIF, that's the initial solution gas oil ratio, again, is a constant. And then at the end, BG is calculated as 1 over capital E, and E is defined as a gas expansion factor, which is equal to the gas volume over gas actually expanded from the cell. We will go over these terms and how to calculate these constants when we were doing the lab. So this was just a quick summary of what we are going to do, and in the next video I'm going to walk you through the step-by-step calculation for our experiment. Okay.